do what they need to do. And I want to welcome all of you to this talk about the night sky. This is of course, our Armchair Travel series. I love having you, all of you people here who are armchair travel enthusiasts. I just want to give you a quick reminder that there is no armchair travel next Monday, the 21st. There is an armchair travel on the 28th, and that is on Japan. Just as a quick reminder too, you need to register for each armchair travel individually because they are each separate. You guys mute yourselves if you're not already muted. Please mute yourself. So I'm not listening to you. Not that you're not charming. Okay, so I'm gonna
finale of Beethoven's Symphony Number 9.
Need you to mute yourself.
On the lower left.
All right. It's a long process, you guys. Please mute yourselves. Okay. So I would like to give you a quick intro to the people who are speaking tonight. So we have Marsha Wilcox, Kevin Boucher, and Joe Geiger. They're going to share their passion for astrophotography in the Aldrich Astronomical Society. Marsha is a retired epidemiologist. Wow, Marsha, that's actually very cool. And avid photographer both during the day and after the sun sets. She photographs the wonders in the heavens using telescopes and dedicated astronomy cameras. She lives in Acton with 3 wonderful golden retrievers. Kevin, a retired software consultant, has been photographing the night sky for more than 20 years. His roll-off roof shed allows him to easily make photographs when the sky is clear. That's very cool too. Kevin leads the astrophotography group and is a lifelong resident of Gardner. Joe has been doing astrophotography for more than 25 years using both film and digital equipment. On clear nights, Joe can be found at the Bear Path Observatory in Clinton or other dark sky sites enjoying the night sky. Take it away, you guys.
Excellent. Let me share my screen. Okay, I think this will do. So let's try this and see how it goes. All right. Okay, what are you seeing right now? Are you guys there? What are you seeing?
I'm seeing your front page. Sky.
We're muted. It says timing. Night sky.
Oh, no. Okay, can you see the title slide only right now?
Yes, that's all I can say.
Yes, okay, excellent, great. All right, good. Well, thank you for joining us tonight. It's my privilege to be doing this talk with Kevin and Joe. Kevin runs the astrophotography section of the Aldrich Astronomical Society, and I've been grateful for all of his advice over the last bit.
Turn that off.
Okay. So let's start close to home in our own atmosphere. This is the Northern Lights, otherwise known as the Aurora Borealis. And this happens when there are sunspots. So the sun becomes active.
A chair from the dining room.
Solar wind happens.
I think I need.
All mute yourselves, that'd be really good.
Bring in the one right around the corner on wheels.
You guys could.
Oh, that's the best one ever.
Steph, can you take care of that?
Or is it out in front?
Stephanie,
Here. Right around the corner.
can you? So, Steph, can you mute everybody? Are we good? All right. So I'm going to keep going here. So anyway, so sunspots cause the Aurora Borealis. There are charged particles that come from the sun and wind up in our atmosphere, and they result in these beautiful colors and patterns of light. This image is a little bit like a photograph of a ballerina in the middle of a ballet. The colors and the patterns dance and they move.
Hey, good idea.
What's your idea? I would never have heard it.
So
You gotta turn it around.
Here,
though.
it'll
stop
fit
the share
right
for a minute. I'm gonna mute these guys. Okay. All right, good. Sorry about that. That's my parents, by the way. So I muted my parents. Sorry. Let me get back to where we were here. All right. Okay. All right. Sorry for that. Here we go. Take 2. So, okay. So the Northern Lights and the solar wind This is close to home. I'm going to move out to looking out beyond our atmosphere into the heavens. On a good night in a big fireplace, you can see a lot in the night sky. This is the northern end of the Milky Way. It's dark enough that the constellation stars.
All right. Someone has two computers next to each other. Please shut one of them off.
Thank you. Great. Thank you. It's very distracting. Okay, so the constellation stars separate from the star field in the night sky. Oh my heavens. Okay, there we go. And I've added a star map here so you can see things maybe with which you're familiar. On the left is Polaris, the North Star. In the middle is Cassiopeia. That sometimes looks like a 3. Sometimes in the year it looks like a W. Other times it looks like an E. You can see Andromeda on the right and the Pleiades on the bottom. These are all at very different distances to our planet. So astronomers collapse them all onto a sphere around our Earth. And then we have a coordinate system where we can find things and talk to each other about where they are, and importantly, aim our telescopes at them. On the right, you'll see our sun. Our sun is about 93 million miles away. That's 8 light minutes. For context, there are more than 500,000 minutes in a year. We will be talking about things that are light years, tens of light years, millions of light years, and tens of millions of light years away from us. In the middle of this diagram, you can see the Milky Way. You can see the core of our Milky Way sort of on the left side, but the stripe is our Milky Way, our galaxy. Here is our galaxy, or one rendering of our galaxy. It's a grand design galaxy, and it's called that because it has a core and spiral arms. You'll notice there's a bar in the middle of it. Some galaxies are barred spiral galaxies, as is ours. We are down in the bottom there. We are here. We are on the Orion spur of the Perseus arm of our galaxy. Our galaxy is 100 light years across. So what does that mean? If we were to travel at the speed of light, it would take us 100,000 years to get from one side to the other. I'll show you things in our solar system and in our galaxy, and then things that are outside our galaxy tonight. This is our galactic neighborhood. In the middle, you can see our galaxy. That little pink thing is the 100,000 light years across, which is our galaxy. Each of the rings in this diagram is 2 million light years. So if you were to travel at the speed of light, it would take you 2 million years to traverse one of the rings. If you look up to the left from our galaxy, you can see that little orange dot. That's Andromeda, our nearest neighbor. Andromeda is 2.5 million light years away. We'll talk about the extragalactic things at the end of the talk, so put a pin in that for now. All right, a little history. There was a guy called Charles Messier, and I have to tell you, I would love to travel back in time and meet him. I just can only imagine what he was like. He was a comet hunter in the mid-1700s. He would go out at night and search the sky for comets. He was going to make his fame and fortune finding comets. And he would find things and put them in his notebook, and he'd go out the next night and he'd see the same thing. And he'd put his head in his hands and he'd say, I'm not a comet, I have to avoid that. So he made a list of things to avoid. This is his list of things to avoid. It's a cornerstone taxonomy for astronomers. This organization of it shows at the top nebulae. You can see reflection and emission nebulae, and Joe will spend some time talking about that. On the right are planetary nebulae, which have nothing to do with planets. It's a bad misnomer, but those are in our galaxy. At the bottom are star clusters, or cities of stars that are gravitationally bound together. There are about 150 of them that travel around our own Milky Way galaxy. Many of them are globular clusters, and Kevin's going to talk about those. There are some that are open clusters, like the beautiful Pleiades on the bottom right. Outside of our galaxy are, oh, hey, what's going on here? There we go. Outside of our galaxy are other galaxies. When Messier saw these, he thought that they were nebulae, but later on it was determined that no, they're not, they're galaxies. So at the end of the talk, we'll go back and return to our extragalactic neighbors. All right, let's take a look at something we all know well. It's early spring or late winter, if you will, and our friend Orion is in the sky now. Orion rises early, and by the time the sun sets, it's near the zenith, near the point straight above us. You can see the characteristic stars of Orion's belt in the middle. The star on the left, the orange one, is Betelgeuse. There was some news about a while back that it was going to go supernova. It didn't. The star in the bottom right is Rigel. It's one of the brightest stars in the sky. It's Orion's left foot. And in the middle there on the bottom is the sword in Orion's belt that contains probably the best known nebula in all of the heavens, the Great Orion Nebula. So I'm going to take you on the Cook's tour of the things in Orion. We'll start with the monkey head that Orion is reaching for, and then go down near his belt and talk about Casper and the flame and the Horsehead, and finally the Great Orion Nebula. This is Joe's image of the Monkey Head Nebula. Now let me pause to let you know that with one exception, all of the colors that you see are the colors that are in the sky. Our night color vision is terrible. I won't go into why, but it is. The red that you see generally is hydrogen gas, and it's emitting energy. Astronomers are very creative people, so you'll have to use your imagination to see the things in the nebulae. On the left is the monkey's eye, and then his nose and his mouth. It's a profile of the monkey with his brow and his ear on the right-hand side. The part in the middle is a star forming region, and you can tell that because it's brighter and there's more energy in it. This is one of my favorite nebulae in the night sky. It's an image I'm still working on. This is called Casper the Friendly Ghost, or Messier 78. It's a reflection nebula, and the clue to that is that it's blue. If you think about the light around, or the fog around a light, you can't see the fog around a light at night unless the light is on. So it's the light that illuminates the fog. And in this case, it's a star or set of stars that illuminates the dust around them. It turns out that the dust preferentially emits a blue color. You'll notice that there's black, there's also soot, large bands of soot, and Joe will tell you more about it. So that's a dark nebula. And some of it's red, so there's hydrogen gas in there as well. Pay attention to what Joe has to say. He'll tell you more about this. This is the largest reflection nebula in the sky, and it's just above Orion's belt. This is the flame and the Horsehead Nebulae. If you look at the star on the left, that's Alnitak. And the three stars in Orion's belt, this is the lowest of them. The nebula below that is appropriately called the Flame Nebula. And you can see that that nebula is illuminated from within. The light's coming from within the nebula, and it's blocked in some of the places by the soot, by the carbon particles that are in there. So this is an Emission Nebula. The dark part to the right is the Horsehead Nebula. Some people see a snake, others see a seahorse, but it's called the Horsehead Nebula. And this is a really interesting part of the sky. If you look above his head, there's a star there. Stars, like hurricanes, are named with consecutive Greek letters based in this case on their brightness. So this is Sigma Orionis. And it's so bright that that's causing the horsehead to cast a shadow in front of it. You can see how the horse's head is rimmed by the light from that star. The red, as you might imagine, is hydrogen gas, so it's emitting energy. And this piece of nebula is unique in that it looks like there's an interstellar wind blowing the gas in one direction. So you can see the striations behind the horse's head. So it's true that in astronomy, just like any other kind of photography, there's close-up views and wider views and very wide views. If you think about a football game and the phalanx of photographers at the side of the field, after the game, you might see a photograph, the iconic one of a hand grasping a football in midair, close up. And you also might see photographs of 20,000 people in the stadium and the entire football field, and the players look like, ants. Same thing in astronomy and astrophotography. There are close-up views, medium field views, and wide field views. This is kind of a medium field view. Here's a close-up view of the Horsehead. All right. Finally, this is the Great Orion Nebula. This is the sword in Orion's belt. There are 3 nebulae in this picture. The Great Orion Nebula is the round one on the right. Then there's the little one that looks like a bird's head in the middle, and the running man on the left. It's a silhouette of a man running. See if you can see it. Here's another place in which the heavens are very active, some of them violent. The nebula in the middle is crashing into the Great Orion Nebula, which is why the middle part of it is white hot and emitting a lot of energy. It's a star forming region. There's so much energy being generated there that stars are being formed. Joe will tell you more about that. Okay. I'm going to tell you just a little bit. And so we have 2 technical slides. There's mine, and then Kevin's going to pick up for me in a sec. You can see in the picture in the middle shows that the way we make these images, it's not just like you do with your phone or your DSLR, one shot and you're done. It's all a matter of accumulating the light. The little movie on the right-hand side shows how things get better as we add subframes to the final image. There are 3 ways that we do it. One, the easiest way is with what's called a one-shot color camera, like a DSLR. We still make many images and still stack them, but we get all the colors all together. The second way is where we separate the color channels and look at black and white, luminance, the red, green, and blue channels, stack each of the channels individually, and then combine the channels to make an image. Pardon me, those of you who are in urban areas or even suburban areas know that light pollution is an issue. So one other way that we deal with that is to use narrow band filters. The narrow band filters allow us to get a single type of light and only that type of light. So for example, hydrogen alpha is red. And when I use that filter, I only capture the color that comes from hydrogen alpha in the sky. So I don't get the moon, I don't get my neighbor's front porch, I don't get my other neighbor's bright light coming out of their house. The cars don't make a difference so much. And again, those are combined and in each channel, and all the channels are combined to make an image. So you've had a cook's tour of our galaxy, extragalactic things, a bit of history, a tour of Orion, and now Kevin's going to tell you about our solar system.
You want to hear about the solar system?
Yep, from Kevin.
Do you want to hear about the solar system?
If you could mute
No,
yourself,
Michael.
great.
It's just starting.
Could you mute yourself, please, Kevin? Kevin?
I'm here.
Hey, okay.
All right. Well, hi, everybody. So I'm going to talk a little bit about some planetary pictures, so basically taking pictures of the moon, the sun, planets in our solar system. And what I wanted to start out with this slide here is if you look on the right, you can see it's kind of talking about the different temperatures in our atmosphere and the fact that our atmosphere has got a lot of different layers the higher you go up. The winds are all blowing in different directions. Marcia, can you make sure that video is running on the left side?
Here we go.
So basically, if you look at this video, this is actually a video that was taken with my telescope of the moon. And you can see how it kind of pulses. It looks like it expands and contracts a little bit. It looks like it shifts left and right. And that's all happening because of the atmosphere. So we take pictures of the planets and the moon and the sun in a different way typically than you would with deep sky objects like nebula and galaxies. And the reason for that is we're trying to take a whole lot of pictures in a short amount of time, because when you're taking pictures of the moon and the sun and the planets, they're very bright objects. You don't need to take long exposures. So what we do is we take a video of the target, like you're seeing here on the left. And what we do is we use software to analyze every frame in that video and decide which ones are the best frames and which ones are the bad frames. The best frames are when we have the atmosphere steady above us for a short period of time. And the worst frames are when the wind's really blowing hard at various levels. And that's where you're going to get a lot of blurring. So what we do is we use the software to rank all the frames in our video, and we use the best 10%, let's say, of all the frames in the video. And quite often for a 2-minute video, we'll have a couple thousand frames of our target, and we only use maybe 100 to 200 of them. And we do the processing the exact same way that Marcia was saying, where we stack the good frames and we create our pictures. So Marcia, you can advance to the next slide. So here's a picture that Marcia took. She can speak to it better than I can, but this is a picture of the moon. As you can see, it's got a lot of beautiful details in it. Marcia, I would guess that you took this with your DSLR?
I did not. No, this was with my one-shot color dedicated astronomy camera.
Okay, so this is a video also.
Actually, it's not. These are short. I forget how many. I don't know, 20 or so frames.
Okay, great. So quite often these pictures that we take of the moon, the sun, and the planets are very, very short. I mean, you only need to have less than a second exposure of each frame. So we don't need to worry about taking like 5 and 10 minute exposures like we do for the galaxies and the nebula and stuff, because they're so bright. Next frame, Marcia. Here's a picture that I took a very long time ago of the moon, very close up, and this was taken with a video camera. You know, it is a little blurry, and this is in the early days of me learning how to do all this, but you can really zoom in on the planets with a telescope. This was taken with a Meade LX90 telescope at a focal length of about 2,000 millimeters. So you can really zoom in and you can see a lot of surface features. In this case here, this is an area of the moon that's showing basically that smooth section in the middle of the picture is what's called Mare Humorum, which is really a big lava plain. You know, when the moon was getting whacked really hard in the early days, several billion years ago, it would allow lava to come, or magma to come up from under the crust, and it would just pour out over the plains of the moon, and you would get a nice smooth surface like that. The crater on top of it, with 2 peaks in the middle, is called Gassendi, and that's at the very top of that lava area there. So those 2 peaks are probably each about the size of Mount Monadnock, believe it or not. They're both fairly large peaks. So very, very bigger features on the moon than you would think. And that whole mountain range on the right-hand side is all mountains that are similar in size to the Rocky Mountains, believe it or not. So, you look at surface features on the moon, you can be amazed at just how big, some of the surface features are that you're looking at. There's a question that came up that is basically asking, what is the image resolution? I don't remember what the image resolution would be, and I have to compute that. I don't know. I don't have an answer, a simple answer for you there, unfortunately. You can move on, Marcia. Here's a picture of the moon taken by Joe Geiger. Joe can speak to this picture himself, but basically this is during a lunar eclipse. And you can see it's got this orange color to it. And the reason for that is, even though the Earth is actually shading the moon during a lunar eclipse, light goes through our atmosphere and refracts the light so that it actually casts an orange color on the moon. And pollutants in our atmosphere factor into a certain degree also, but it's really the way the light is refracted through our atmosphere. So it's very bright at the top because it's not quite a perfect shadowing of the Earth on the moon, but it's still a beautiful picture Joe got here. My guess is he got this with his DSLR camera. Next
That's
frame.
correct, yes.
So this is a picture that I took. Me and my wife and a bunch of members from Aldridge Astronomical went out to Idaho during the 2017 solar eclipse. We went out to Idaho because primarily that was a location that we were most likely not to get cloud cover. We were on the on the western slopes of the Grand Tetons. You can see the Grand Tetons at the bottom of this picture. My wife took that picture actually while we were in the middle of the total eclipse. And what's cool about a total eclipse, for those of you who've never seen one, and I very highly recommend you try to catch the 2024 eclipse, April 8th or 9th, I forget which one of those dates, in 2024. It's going to run from Texas up through northern New England. And this one here was about 2 minutes long. So for 2 minutes, that center picture of the sun being completely eclipsed by the moon is what you see with the naked eye, which is really amazing. And what you're seeing, what looks like a sunset in our picture of the Grand Tetons, well, that's what the sky looks like 360 degrees around you. Because if you look straight up, you can see the stars. But if you look all the way around you, you're in the moon's shadow. So it's an absolutely beautiful, amazing event. And what's cool is that you can look directly at the sun while it's in totality, but when it's partial, like you're seeing in the other 4 segments on each side of the sun here, you cannot. You need solar glasses to look at it. So this is a composite photo that I put together to kind of get a sense of both the full eclipse duration and the sense of place that we were at the time. You can go to the next slide, Marcia. Here's a picture of Comet Neowise that was went through our skies last year. Joe Geiger got this photo. It's a beautiful photo. And basically a comet, as you probably know, is a transient, basically, object in our solar system. They can range in orbit length from anywhere from few years all the way up to tens of thousands of years if it goes all the way out to the Oort cloud. And what happens is volatiles on the surface of a rock basically get basically gasified from our sun's solar rays, and it creates this comet tail that you see here. Basically, that comet tail is always the opposite direction pretty much from where it's, where it's heading towards the sun, so that's what's causing that tail. And it's really just a lot of dust and gas debris that's coming off the surface of basically this rock that's traveling through our solar system. So next exposure. This picture was taken by Len DePinto. He may even be on this call.
Yes.
Beautiful picture. Len took this with a good sized telescope. The thing about astrophotography for planets is that, planets are very, very small when you're looking at them through even a big telescope. So the bigger the telescope and the most magnification that you can possibly get, the better off you are in terms of seeing surface details on the planet. So here you see it's a composite photo that Len took. All these planetary pictures were all taken at different times, but he put them together for a really neat photo of Mars on the left, Jupiter in the middle, and Saturn on the right. And you can see some great details in all of these photos. Once again, he did this with a video camera. Yeah, next one, Marcia. This was taken by Marcia. This is a great nightscape photo of the Milky Way. And you probably, those of you who live in the Concord area, probably recognize the Old North Bridge there. What's great about nightscape photos is that you get to include a terrestrial object that you're framing with the beautiful night sky. So you can get some really cool pictures, and you'll see a lot of nightscape photos, people taken maybe over the Grand Canyon or in Yellowstone or wherever around the country, are very recognizable terrestrial objects with beautiful Milky Way objects. So Len, you probably said that the planetary images are 0.2 arc seconds a pixel. So very, very, very fine resolution. This picture here, Marcia, you can say that this is in Maine, on the coast in Maine.
Yeah, it is. Yep. This is in Maine in a dark sky place. And the lumpy part of the Milky Way on the right-hand side over the trees is where the core of our galaxy is.
Yes, that's where Sagittarius would be. Beautiful, another beautiful shot of the Milky Way. Taking pictures of nightscape photography over the ocean is a great place because you typically get dark skies over the ocean. So you're allowed to get beautiful pictures like this, beautiful panoramas. And the ocean acts as a great reflector, for, what you're seeing in the sky. So you often get really stunning photos as a result. Next photo, Marcia.
Great. I think we're going to turn our attention to star clusters.
Okay, so let's talk a little bit about star clusters before we get into them. There are two different types of clusters. As you can see, they're mentioned down below here, globular and open. And we're going to see pictures of both coming up here. Globular clusters are groupings of stars, very, very tight groupings of stars. Typically, you're going to get anywhere from like 20 or 30,000 stars all the way up to close to 1 million stars in the largest globular clusters. The stars are really, really close together. They're going to look like a pile of diamond dust. And what's cool about them is globulars, unlike open clusters, are very, very old. They were formed in the early days of our universe. So most globulars are close to 10 billion years old. So they're very, very old stars. And this is a sample of a globular cluster called Messier 13. You'll find globulars close to the center of our galaxy, and that's where this one is. It's 25,000 light years away from us. And you can see it's just got an absolute ton of stars that really coalesce into a core of really dense cluster of stars. If you lived in a solar system around one of the stars in the center of this core, you would never have night. It would be daytime pretty much all the time because there are so many stars in your sky. You would never get dark enough to have a dark sky like we have. Next one.
I just have to say how much I love this image. It's hard to get resolution of the stars in the center of this particular star cluster. And Kevin's done a beautiful job showing us both the blue young stars and the yellow older stars.
So this star cluster, this globular cluster, is very close to the one that we just saw. It's called Messier 92. Someone's asking, do globulars rotate? The answer to that is they do move and they do rotate some. They are gravitationally bound to each other. What I mean, the stars within the globular are gravitationally bound. And unlike open clusters, which are not gravitationally bound, our solar system was born in an open cluster many, many, many millions of years ago. And the siblings of that cluster have kind of dissipated over time. So they've all gone in different directions. Whereas globular clusters, since their stars are so close to each other and it's such a large gravitational mass, they generally stay together. Next slide, please. So the next cluster we're going to show you is the Pleiades. You can see if you follow the belt of Orion at the bottom of the picture here, it goes over towards Taurus, which is where we're going to find our Pleiades, which is M45. And this is what's called an open cluster. You can see the stars, there's less stars. They're much younger. I mean, open clusters are generally groupings of younger stars that were born in a nebula. And basically, I'm just going to shut off my alarm here. They will gravitationally, they're not really connected to each other, so they will dissipate apart from each other, drift apart from each other over time. There are some absolutely beautiful open clusters like this one, Messier 45. Now, believe it or not, the nebulosity that you've seen around these stars are not the nebula that these stars were born in. This is interstellar dust that this traveling group of stars have run into and are just lighting up to make a beautiful picture. So this is something that you can see with the naked eye. You will see like a fuzzy thing up in the night sky. This is something you can see this time of the year, and you can see it with the naked eye. You don't even need binoculars, but binoculars would be a very good thing to use when you're looking at something this large in size. And
yeah, this is one of the closest objects you'll see. This is 444 light years away, which is very close compared to everything else.
everything else, yes.
Good. I think we'll turn.
And also, if you drive a Subaru, this is what the
yes.
Subaru is named after.
7 systems, correct?
Yep. 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 You might be able to count some of the stars if you're in a dark enough place at night. All right, Joe, will you take us through some nebulae?
Let me dust off the slides here. So we've talked a little bit about the beautiful dust, and so I'm first going to give you a couple of examples of these. So Emission nebulas are actually, as the name suggests, are nebulas that give off energy. So at some point, the energy from a star or energy from star creation ionized the molecular clouds, and they emit light in different frequencies. And typically they're red in color. There are some other ionizations that occur at oxygen 3 is a more bluish color, bluish green color, but they are typically red in color. Planetary nebulas are emission nebulas, but the difference is that a planetary nebula happens when a red giant expels its outer shell of gas. And so when it does that, there's a lot of energy, and that energy is transmitted into the gut gas and the dust. And so it usually is it's from a dying star, whereas the emission nebulas are typically where new stars are born. So emission nebulas are both at the beginning of a star's life and what they're formed from, and they occur at the end of a star. And planetary nebulas are often multicolored. The name planetary is a misnomer, though, because they're not really named. They have nothing to do with planets, but that's just the name that they gave them. A reflection nebula, as was discussed before, is a collection of dust that's really lit up by the stars that are nearby, and they are typically blue in color. And if you had a dark nebula in front of a star, it might, and you look at the backside of it, it might hide that star. So dark nebulas are actually non-ionized clouds of molecular clouds of gas and dust that block the light from our perspective here on Earth. If you went, if you got in a spaceship and traveled to the other side, you might actually see what's behind it, and there may be lots of bright stars, but because that gas is so dark, is so dense, it blocks the view from our perspective here on Earth. So those are the main types of 4 types. This is an awesome image that Kevin took, and it's of the Ghost Nebula, and it's about almost 1,500 light years from Earth. And as you can see, there's it looks like very ghostly figures in here. And this is I love this image because it reminds me of Halloween. This is an example of an emission nebula, and this is the Rosette Nebula. And Marcia took this. This is about 5,200 light years from Earth, and in the sky, one of the things about nebulas is that they can be very small or they can be very large. This nebula, if you could see it with your naked eye, would be almost the width of 4 full moons. So it's pretty large in the sky. But because it's so far away and it's pretty dim compared to like bright stars, we can't see it without the aid of a telescope or a camera that can capture the photons over a long period of time. Now, for these kinds of exposures, for nebulas especially, as you saw before, you want to stack a lot of images. So, typically to get good signal to noise ratio in these, you're going to want, at least 3 hours, but you'll get even better signal to noise and a lot cleaner images if you capture longer than that. So Marcia, how long did you capture this one for?
This was, I think, 3 hours, but this was done with a very fast telescope. So some telescopes are f10.
Yep.
This was with an f2 telescope, which is 25 times faster than an f10.
So it can capture that much more light in less time.
Yeah, very
Next,
interesting
please.
thing about this is there's a star cluster in it in the middle. Yep.
Oh yeah, then there's so this one also has a star cluster in it. Now this is the California Nebula, and I took this one a couple of years ago, and the star Menkeb is the bright star right to the left of that, or to the right of the nebula there, and they think that star gives off, it's such a hot, dense, bright star that it actually ionized the gas to form this nebula. And this nebula is pretty large. This one, even though it's 1,000 light years away, it if you could see it, it would be, you know, it would be pretty large, like maybe 2 full moon widths in the sky, or one or 2 full moon widths in the sky. And another thing, this was taken with an 80 millimeter telescope, and so that is more of a wide field telescope. I know Kevin has a what's the focal length of your telescope, Kevin?
Well, I have 2. The big one is 2,000 millimeter. That's
Yeah.
like a 10-inch telescope, and I also have an 81 millimeter refractor. So, which is about 380 millimeter. It'd be equivalent to like a 380 millimeter camera lens.
Yeah. And so you, as an astrophotographer, just like you would with a camera, you might use a telephoto lens to get close to an object, or you might use a wide angle lens to get more area. And so that's what we use different size telescopes for. So there is an Einsteinian formula for the optimal number of telescopes, and that is X equals F plus 1, where F is the number of telescopes you currently have. So that's a astrophotography joke right there. I'm sorry. It's late here. Okay, next slide, please. Now this is the Heart Nebula, which is located in Cassiopeia, I believe, or near Cassiopeia. And this is also an emission nebula. And this also has, as you can see, there's some nice star clusters right in the middle of that there. And this is actually 2 nebulas in one. It's the Heart Nebula, but if you look to the left there, you'll see what looks like a fish head, and that is called the Horsehead Nebula. So it's part of the Heart Nebula. And Marcia took this photo. Was this with the fast f2 scope as well, Marcia?
Actually, it wasn't. This was with my guide scope because my main scope was in California on sabbatical.
Oh.
Be repaired. So this was with a 355 millimeter, my guide scope, basically.
And then the next one, the next image is the Soul Nebula, and these two are right next to each other in the sky. Again, this is an emission nebula like the Heart Nebula, and it has it's made up of some star birthing regions with some open clusters in there that you can see. You can see where the energy is hotter because that, like Marcia said before, that is where the dominant star creation activity is. That's where the dust and gas is coalescing into stars. Next image, please. So we're going to look at some nebulas now in Cygnus, and there's quite a few of them. So the first one is I believe is a wide angle shot of the heart of Cygnus the Swan. So the star right in the very middle, or kind of in the left middle there, that is Satyr, and this is an intense region of star formation in the constellation Cygnus. And I took this to give you I took this with my 250 millimeter focal length telescope. So it's wider field of scope than even an 80 millimeter telescope. So for example, my 250 millimeter telescope could fit both the Heart and the Soul Nebula into it. So you're looking at a lot more sky with a shorter focal length telescope, and you're looking at a lot more magnification with a longer focal length telescope. And also, if you're interested in getting into astrophotography, you might want to start with a smaller focal length telescope, because it's a lot more forgiving with guiding errors and alignment and things like that. Whereas when you have a lot of magnification, any little misalignment or guiding error will be easily seen. And in the right hand corner of this, you'll see the Crescent Nebula, and there's a close up of that in the next slide here. And this the Crescent Nebula is actually two solar winds that are opposing each other and causing this kind of rippling effect. It looks kind of like a jellyfish, but it's actually solar winds. There's a star in the middle of it that is causing the gas and dust, and then there's solar winds blowing kind of from opposite directions that give it this kind of jellyfish or crescent look to it. And this is about 5,000 years away. So if you went out and looked up at the sky, you wouldn't see this. You really need to have long exposure photography to see these things. Next, please. And this is the Cocoon Nebula, and this is a great example of not only an emission nebula, but also if you look around, you'll see that the gas is obscuring. You'll see dark patches, and this is also a good example of the gas and dust obscuring the light from behind those clouds. So it really makes this nebula pop, because it's like sitting on sitting in it like a bed of gas and dust that really bring this out visually. And this one is about 3,200 light years away.
Kevin made this. It's a gorgeous image. Just want to say
it's very beautiful. Yeah. And so this is a beautiful image that Marcia took of the Veil Nebula, and this is the entire east and west Veil Nebula. And what you'll notice particularly about this is that it doesn't have it has one star, the really bright star. And some of the processing software that we use is able to look at an image, and it's able to look at an image and then take the stars out of the image. And this allows us to focus on removing the background noise and actually and processing and color correcting the nebula image. And in some cases, you can add the stars back in, or in this particular case, this looked so beautiful that she left the stars out. So the processing software that we have is very powerful and very capable of using machine learning and artificial intelligence to know what's a star and what's not a star. If the next example is the Western Veil Nebula, which is the part that we saw before, and this time the stars are added back in. And so you can see that it's in a very dense region of the sky for stars, and this is only about 1,500 light years away. This is also called the Witch's Broom Nebula, because it kind of looks like a witch's broom, and these are pretty big overall in the sky. So with the previous image, Marcia, was that taken with your guide scope, or was this a mosaic? How did you do this one?
Yeah, this is a mosaic.
Okay.
So multiple panels. I wanted to look at the filaments in the nebula.
One thing to note on this picture, so that everybody knows, this is created from a star that exploded. And what you're seeing there is really an expanding gas shell. I believe this star, the star that created this supernova remnant, which is what this is, blew up many, many thousands of years ago. And so what you're seeing is the remnants of that star basically just expanding out in a big shell.
Yeah. Okay. This is also part of the Veil Nebula, and Kevin took this. Do you want to talk about this a little bit, Kevin?
Yeah, sure, if you like. This was taken with narrowband filters. I used an oxygen 3 filter for the blue color in a hydrogen alpha filter for the red color. This was taken with my largest telescope. So it's a very, very zoomed in area of the Veil Nebula. It's called Pickering's Triangle. It's got that kind of triangular shape to it. But what's cool about it is that you can see all the wispy filamentary details of the gas that's just sitting out there and getting lit up by, you know, the stars in that area. So, but once again, this is literally the remnants of the supernova, and the shell is just expanding and expanding and getting bigger all the time. So,
Great. So we move on.
Yep. This is the Tadpole Nebula in Auriga, and this is also a star birthing region. And the tadpoles are formed when a star is there's a lot of energy coming off a star, and the jets. It actually jettisons out gas. It's like the star burps as it's kind of being formed, and and so it creates these jets that come out of the birth of where the star is being born, and so that's what gives it the kind of the tadpole look to it. This image I took on my back deck, and it uses I use a one-shot color camera, but I use a special 2-band narrowband filter that blocks out all but the hydrogen alpha and the oxygen 3. So I can get a lot of the advantages that you can get with a monochrome camera with narrowband filters, but I can do a lot of that's almost not quite the same, but pretty close to the same kinds of imaging that you could do with narrowband filters and a mono camera. And so this image is actually made. That's how this image was made from that. And again, you can see there's star cluster inside this nebula here, where and you can see where there's higher energy, where those stars are being born, and you can also see in the holes in the middle of it there, that's the black sky behind it, or even gas and dust that are behind it that are obscuring the sky from behind it there. So this is the Bubble Nebula, and this is when I first saw this, I couldn't, this nebula, I didn't really think it existed. It didn't look like it was real, but this is not necessarily a dying star. This is again a star birthing region. There's just a lot of gas and dust in here that happen to form this kind of bubble region around that area. And this is a fantastic picture. Was this Marcia? Did you take this with your C11?
11, yep, yeah.
Yeah.
So for the equivalent camera lens is 3,000 millimeters.
Yeah, so almost 3,000 millimeter camera lens.
We should move along if we can.
Yep. Next one, please. These are nebulas you can actually see with your naked eye or a good pair of binoculars in the summer. If you go out to the constellation Sagittarius and you look up for the teapot, the steam coming out of the teapot in the constellation Sagittarius, the steam is actually this region here. This is the Lagoon Nebula, which is the big one in the center, and then the Trifid Nebula. And I used my wide field telescope again to take this picture. And if we go to the next photograph, Marcia used a higher focal length telescope to take just a picture of the Trifid Nebula. And what's interesting about the Trifid Nebula is that it has Emission Nebula, Reflection Nebula, the blue is the reflection, and it has a dark nebula, all encased in the same object. So it's a bundle right there. You get a lot for your money right there. And then this is a reflection nebula, the Iris Nebula. And it is, again, about 1,300 light years from Earth. And someone's asked, how do you know where to aim your telescope? Well, you first, you kind of have to learn where the objects are. Today's computerized telescopes let you cheat, but I would say the best way to get to know the sky is to get a pair of binoculars, and you can see a lot of objects with a pair of binoculars, and you'll get to know your way around the sky and where these objects are. And then once you know that, then having a computer makes it easier and faster to take images and to be more efficient about it. But it's good to learn the sky without the computer help at first, because then you know it much better. Next, please.
They have coordinates on the celestial sphere, which is also.
Yeah, and there's coordinates on the celestial sphere too. This is the Christmas Tree Nebula and the Christmas Tree Cluster. And again, this is Marcia always says she's taken some creative liberties with the colors in this, but I kind of like it. It looks very Christmassy.
Thanks. There's no green in space, but there is a Christmas.
Yeah, there is in this though. Okay, now we're going to look at some planetary nebulas. And the interesting thing, as I mentioned before, planetary nebulas are really exploding stars, or stars that have exploded off their outer shell of gas. And what you'll see with these next series of photos is that they come in different shapes. So this is a picture of Able 39 that Kevin took, and it's very round. It almost looks like a bubble. If you go to the next photograph, you'll see that this is the Dumbbell Nebula, and you see that dumbbell shape. And if you were to take that dumbbell shape and turn it towards you, you would see a round, you would see it as a round shape. And so when in some planetary nebulas, when they explode, they tend to explode in lobes. And so in this nebula, you can see the lobes, you can see the dumbbell shape. If you go to the next picture, this is kind of a different view. You can sort of make out the lobes a little bit, but it's more of looking down the lobes into the explosion. And this is called the Headphone Nebula, and this is about 1,600 light years away. And again, these are emission nebula that are dying stars that ionize the gas as they blow off that outer shell. When they're dying, it ionizes the gas with hydrogen alpha and oxygen 3, a lot of oxygen 3 in planetary nebulas. Next, please. And the famous Ring Nebula. And so again, if you're looking down the lobes of the Ring Nebula, you're looking down the center, and in the center of it, you can actually see the star that's exploded off all the gas and dust. This is a pretty famous planetary nebula, and it's usually a favorite of people when they first start going through the Messier objects and finding the Messier objects. It's in the constellation Lyra.
Great. Thanks.
So those are the nebulas, and now Marcia's going to talk to us about galaxies.
Okay, we're almost at 8, so I'll give you the Cook's tour of galaxies. I'll try to keep it just for not too long over, but it will be a couple minutes over. Hope you enjoy it. So we've looked at things in our own galaxy, in the Milky Way, and now we're looking beyond our galaxy. We're looking at island universes that are outside of our own Milky Way. There are many, many different types of galaxies, and I'll introduce you to them as we go through. This is a star map to show you where Andromeda is. If you find Cassiopeia in the night sky, Cassiopeia will point you to Andromeda. And if you can find the square that's Pegasus, you can also get there by going left. And here it is. This is Andromeda, our nearest neighbor galaxy. Andromeda is considerably larger than our own galaxy. And it's also very far away. It's 2.5 million light years away. So what does that mean, 2.5 million light years? Well, when the light that hit my sensor left the galaxy, It was a stone age. Homo sapiens didn't yet walk the planet. Another thing to take a look at is that this galaxy is not quite face on. So if you think about holding a coin in your hand, you can hold it face at you so you see the head or the tail, or you can hold it edge on where you only see the edge, or you can tip it one way or the other. And that's what's going on with galaxies, or with our images of galaxies from our vantage point. It's true that almost all galaxies are interacting, and Andromeda is interacting in a big way. The little tiny galaxy up on the upper left is Messier 32, and that's interacting with Andromeda, as is Messier 110 below it. But put a pin in that, there's more about Andromeda and what it's influencing. I love this. Kevin, do you want to spend a sec about this?
Yes, this is a composite picture. The galaxy picture I actually took, once again, this is the Andromeda galaxy, quite, a number of years ago, but the picture of the Devil's Tower was taken on our trip out west to go see the solar eclipse in 2017. So I thought it would be kind of cool, touching on close encounters of the fourth kind or whatever, and make a picture like this that has that nice terrestrial object that people know well, and then I basically, using Photoshop, put the Andromeda galaxy photo that I had right next to it. So I thought it was kind of a cool shake on things.
I like it. It's art and science together. Kevin also made this wonderful photograph of the Whale Galaxy. It's an edge-on galaxy. You can see the dust lane going down the middle. The new stars are blue, the older stars are yellow in the middle. If you look at the pink star up top, that might be his eye, and then the fin beneath that. This galaxy is interacting with others. You can see the one sort of by the belly of the whale. So there's a lot going on in space. It's quiet and serene at night, but there is a lot of activity and energy and almost violence going on in the heavens above us. Kevin made this wonderful image of the Fireworks Galaxy. It's a face-on galaxy. It's a spiral galaxy. It's about a third of the size of the Milky Way. And this galaxy, like the others, is interacting with the galaxies around it. You'll notice that the spiral arms are not nearly tightly wound as our own Milky Way galaxy. This is Joe's beautiful image of the Triangulum Galaxy. The Triangulum Galaxy is the second largest galaxy in our local group. So it's, as things go, not far from Andromeda. But you know now from what Joe's taught you about nebulae and things, that the pink spots in here are nebulae in that galaxy. You can see the dust lanes, and you can see that the arms of this galaxy are not, they're a lot looser than the arms in the Milky Way. Sad for them, this galaxy is going to interact with Andromeda in about 2.5 billion years. But wait, there's more. Andromeda is going to collide with us 1.5 billion years later. So there's a lot going on in our local group, a do-si-do that takes billions of years, Andromeda and Triangulum, and then that combined galaxy with us later on. It's evident in Joe's image of the Pinwheel Galaxy that something's amiss. It's not symmetric. The reason it's not symmetric is that it's interacting with a nearby galaxy that you can't see in this image, but you know enough now to know that the pink dots are nebulae that are local to the Pinwheel Galaxy, and the dark spots are the dust lanes. The carbon, the soot that define the arms of the galaxy. Here's a quick map of where the pinwheel is. The Big Dipper, the bowl of the Big Dipper is headed off the top of the screen, and the handle of the Big Dipper is pointed straight down. So the pinwheel is at the left side of the handle, and the whirlpool, the last galaxy we'll look at tonight, is on the right. When I look for the whirlpool, I always look for the Dipper. Astronomically, it's in the same space as the Cannes-Venatici constellation area. But for me, I see it in the Big Dipper, otherwise known as Ursa Major. And here it is. This is from my driveway in Acton. These two galaxies are interacting with one another. The little galaxy, according to those who know way more than I do, has been through the big galaxy and is being pulled back again. So they're doing this galactic do-si-do. The two galaxies interacting with one another. So thanks for sticking with us. So what we've hoped to, what we showed you tonight a little bit is from the inside out, looking at our own solar system. Kevin showed us the moon and the planets and one of Joe's comets, and then talked to us about cities of stars, globular and open star clusters. Joe took us through beautiful dust, looking at emission, the red nebulae, the blue reflection nebulae, the very badly misnamed planetary nebulae and dark nebulae. And finally, we looked at island universes distant from us. Here's a quick look at how we see them. Kevin's cool roll-off roof observatory and his telescope are the top two. On the right two images are Joe's travel set and his observatory. I'm there on the left, and Len showed us his observatory in the middle. So thanks for sticking with us. And here's our website if you're interested in Aldrich, and that's what it looks like. So if you have questions, feel free to unmute yourselves and we'd be happy to talk to you.
That was fabulous, you guys. And all I'm going to say is you're welcome to stay and chat for as long as possible. I'm going to turn off the record.
Excellent.
So we are done recording.